did this part, right? And let me add a page. So Akib is not here, right? So let me recap what did we learn in this fourth chapter, right? Okay. Yeah. So first thing we talked about was this so laws of right. First thing that we talked about was this inertia that the nature resists the change, right? So if the object is in motion, then the object will continue to be in motion. And if the object is at rest, then object will continue to be at rest. So that is the ability of the object, right?
Yes, sir.
So then we got the idea of the external force. Then we got the idea of the force that whenever whenever the state of the object is changing, which means that there is some force which is acting on that object, right? So first
Yes,
thing
sir.
that we learned in that, so this gave the idea of the force, right? So law of inertia, which is the first law of motion, right? So this is given by Newton itself, right? And first law of motion talked about this law of inertia, right? So until and unless there is some external force applied on that object, then only its state will change. Otherwise, it will continue to be in that state, right?
Yes, sir.
And second thing that we learned in the laws of motion was the second law of motion, and which said that the force is directly proportional to the rate of change of momentum, right? So this is the average force, and when we remove this proportionality, so this would be delta p by delta t, and when we calculate, right, when we calculate the instantaneous force, so this would be dp by dt. This is the thing that we learn, right?
Yes, sir.
And we also defined that what is the momentum. So we defined that momentum is mass into velocity, right? So this term gives the idea of the inertia, right? So this term is the measure of the inertia, right? So now let's say that if we put the value of P in here, so this would be d by dt of m and v, right? So let us write only the
Yes, sir.
magnitude part. So this would be first we take the differentiation of, we take m outside and we take the differentiation of v, and then we keep v outside and then we take the differentiation of t. Remember, there is no cross product. That is why I can write it in here. Because as you saw in the evening, that if we have something like this, then we have to write, if we write the differentiation, then we have to write first dm by dt cross v plus m cross dv by dt. right? If we have, let's say this is some other,
Yes, sir.
right? So if we have this cross product, then we have to write the differentiation like this. But if this is not a cross product, then we can write this v in anywhere, right?
Yes,
Okay.
sir.
So what is this term is telling? That your mass is changing with respect to time. So does this happen in general scenario? Does the mass changes over time?
Yes, sir.
Yeah, so mass changes over time. So let's say that you have a 2 kg object and that object is moving with some velocity. So will the mass of that 2 kg object will change? Will it become 3 kg or 1 kg? Yes. What will
No,
happen to it?
sir. It will.
So which means that this is constant. So you remember what is the differentiation of a constant quantity? What is the differentiation? Let's say if I ask you that what would be d by dx of 4, what would be this? Yes.
So,
So in the differentiation rule, we understood that whenever we take the differentiation of a constant quantity. So differentiation means what? We are calculating the change, right? When we change this x, will this 4 will change?
no, sir.
Right? So which means that there would be no change. So which means that this would be 0, right? So whenever we calculate the differentiation of a constant quantity, so that would be 0. Understood?
Yes,
So
sir.
this is a constant, so this will give you 0. So then you have this m dv by dt. And what is dv by dt? We have discussed so many times. What is dv by dt? Rate of change of velocity. Yes, what is dv by dt? Allow
So, dv by dt is acceleration.
acceleration, right? So this will become m and dv by dt is acceleration. So you will get force equal to m. So you from the second law of motion itself, we get force which is equal to mass into acceleration, right?
Yes, sir.
So this is how we get force which is equal to mass into acceleration. And then we understood about the idea of impulse, right? So impulse was force into time, right?
Yes, sir.
So yeah, this way, this impulse was force into time, and then this impulse was also this change in moment, which was p final minus p, right? So this was the impulse, right? Okay,
Yes, sir.
and we also saw that yeah, so we also saw that from the third equation or from the third law of motion that forces are equal and opposite, right?
Sorry, sir.
So forces are equal and opposite, right? Whenever this let's say you strike a ball in this wall, then it will apply the same force on this ball, right? So the
Yes, sir.
forces are equal and opposite. Action and reaction are equal and opposite. This we learn from the third law of motion, right?
Yes, sir.
Okay. So from here we saw that right? So from here we saw that this would be this F12, right? And this is minus F21. So this would be D P by, let's say this is P12 by dt, and then this is d P21 by dt, right?
Yes, sir.
Okay, so from here, okay, let us leave this part. So from here we got the conservation of momentum, right?
Yes, sir.
Conservation of momentum, which said that your P initial would be equal to P final, right? So this was the idea of, and this we get from the third law of motion, right?
Yes, sir.
Okay, and after that, what did we learn? We learned about the equilibrium condition, right? In equilibrium condition, we saw that, let's say there are three forces, right? There are three forces acting on this object, and let's say in here, and in here, right? So let's say this one, and this one, and this one, right? Three forces are acting.
Yes, sir.
So which means that if this object is at equilibrium, then all the forces will add up to give
On
you,
the same point.
yeah, so then all the forces will add up to give you zero, which means that F net would be zero, right?
Yes, sir.
So if your F net is zero, then which means that your dp by dt, or your mass into acceleration is zero, right? So
Yes,
mass
sir.
mass can never be zero, so which means that A is zero, right? And
Yes,
uh,
sir.
and for what condition acceleration is zero? So acceleration is zero in two cases. One would be that the object is at rest, right? Then your acceleration would be zero. Or it also happens that your object is moving with constant velocity,
Yes, sir.
right? So when the object is moving with constant velocity, then what will happen?
Uh, Acceleration will be zero.
Right, because there is no change in velocity, so change in velocity is zero, so acceleration. Good. And then what we did? So then we understood about the common forces in mechanics. Common forces in mechanics, right? So from all these conditions, we understood two things, right? We understood two things, that if the body is equilibrium, then F net is zero, right?
Yes,
And
sir.
if the body is not at equilibrium, right, then your F net would be how much? Right.
Yes, sir.
So these are the two things that we understood. And this is most crucial things that we have to. This one is the most important result that we have to remember, right? Okay. So then we understood about common forces in mechanics, and which was what? So first one was the gravitational force, right? So we understood that every object is pulled down towards the center of the earth, right? So
Yes, sir.
let's say this is the surface of the earth and the object is here. So every object is pulled towards the center of the earth, right?
Yes, sir.
And the force of gravity that is equal to mg,
Yeah, mg is equal to mg.
right? So this was the gravitational, and that is at the surface, right?
Yes, sir.
And and it is always towards the center, right? So,
Yes.
and then the second thing that we understood was this normal reaction, right?
Yes, sir.
Whenever we had two surface which were in contact, right? So let's say this is the earth surface and there is some object which is placed on this earth, right? So
Yes,
then this these two surfaces are in contact, right? So this
yes,
surface will apply a perpendicular force in this direction, right? This surface and this surface also. So this surface will apply a perpendicular force in this direction. So this was called the normal reaction,
yes, sir.
right? So this normal reaction was applied by, so it was applied by the this other surface, let's say this is Earth, right? And then this
Yes,
normal reaction is applied by the object itself. So this is by object itself, right? And when we will do the equilibrium or all those conditions, then we'll know that we ignore this. So whenever we write, when we'll understand about this free body diagram, then we will learn that we neglect all the forces which are applied by the object, right? So
yes,
that
sir.
we neglect. Okay, and so this was the normal reaction. Let's say we have these two surfaces, right? So these surfaces are in contact. So then this will apply some on this surface apply a normal reaction to this side, and this surface will apply a normal reaction to this side, right?
Yes, sir.
So whenever two surfaces are in contact, they apply the normal reaction. This
So
was
what about like uh like on the ground there'll be
yeah.
only two
Yeah,
forces?
yeah, yeah. So this, of course. So there would be another force which is acting because this surface is also contacted with this one. So this will
Yes,
also apply the normal reaction. Yes, absolutely right. Whenever the surfaces are in contact, they will apply the normal reaction. Right.
yes, sir.
Okay. And then the third thing that we understood was this tension. So whenever we have this string, right, with some mass attached,
Yes, sir.
then they will apply some then they will apply some force in the opposite direction of the mass attached. So let's say we have this string and some object is hanging with string, right? So then this string will apply a tension in this direction. right, against the mass of this object.
Yes, sir.
Understand? And let's
So
say, yes,
tension is there for the lift also, right? The lift questions.
yeah, yeah, for because the lift in the lift question, the lift is attached with the cables, right?
Yes, sir.
So those cables have also the tensions.
Okay, sir.
Oh, okay, so then let's say two objects are attached with the some string, and generally we assume that this string is massless,
Yes, sir.
right? And we also assume that this is inextensible, right? So if this is massless, then the tension applied by this would be same, and this would be the same, right? If this would
Yes.
have been massive, then this one would have been T1 and this would have been T2. So this is how we uh, this is how we calculate this tension, right?
Sir,
Okay.
I have one doubt.
Yes.
Sir, so if there are two objects attached by string and one object's mass is more, so will that tension be more than the other tension?
No, no,
Or
no. So no, no, no. So that this object's mass, right? This is M1, then this is M2. But
yes, sir.
this tension, if these are same string, right? If this
Yes,
is
sir.
the same kind of string, then this tension would be the same, right?
Okay,
This
sir.
tension would be the same.
Okay, sir.
Yeah. So these were the forces that we understood, right? And then we calculated and then we understood about this free body diagram, right?
Yes, sir.
And in the free body diagram, we understood that we have to write all the forces, right, acting individually on the object. And the idea is that don't count the force applied by the object,
Yes, sir.
right? And then
Yes,
apply the Newton's laws. So this was the idea, right, of this free body diagram. And
yes,
then we learned about that. Let's say we have, right. Let's say first thing we talked about the combination of the forces. So let's say we want to write the free body diagram of a mass hanging with this string, right?
yes, sir.
So then, what were the forces that was acting on this object?
So tension and gravitational.
Yeah, tension and gravitational force, right? So then, this object is at equilibrium, right? Which means that so this is at equilibrium, which means that F net
F net
was the
zero.
so which means that T was empty, right? So
Yes, sir.
this was the the simplest thing that we understood. And we also understood that, let's say we have a surface, right? So we have this surface, and which is this object which is kept on this surface, right? So this object will experience the gravity and a normal reaction by this surface, right? So then
Yes,
this
sir.
n would be equal to, at equilibrium, this n would be equal to empty, right?
Yes, sir.
Okay, and then we also talked about Then we also had this inclined plane, and then we talked about, let's say, the equilibrium at this incline. So then we had this object, and this was the inclination angle. So we wrote down one, right, weight, which is mg. So this is m. So this is mg, right?
Yes, sir.
And then it had two components. So this angle was theta, and this was. So this mg had two components. This one, right, along perpendicular to this inclined plane, and that along the inclined plane. So this one was how much? Do you remember, Ilham? Yes.
Sorry, sir.
This was how much? This component was how much? Yeah, this was theta. So this component was how much?
So I don't know what is the question.
What is the, okay, so let's say this is theta, this is r. Then along the theta, what is this component?
So cos theta.
R cos theta, right? So this is the question. Along the component, because this mg has two components, right? This
Yes, sir.
is this is the along the plane, and this is the perpendicular to the plane, right? So this has two components. This would be mg cos theta, and this would be mg sin theta, right?
Yes, sir.
And then the other forces which was acting on the surface was this normal reaction, right?
Yes, sir.
So because we know that this object is not moving in this direction, right? This is not moving in this direction. So which means that this force is balanced by something. So this normal reaction is balanced by mg cos theta, right? But this
Yes.
is not, yes?
Sorry, sir.
Yeah, do you have any question? Did you ask
No,
me?
sir. No,
Yeah.
sir.
So this normal reaction is balanced by this mg cos theta, and this one is not balanced, which means that this will slide, right?
Yes, sir.
So if we calculate, let's say this is the acceleration, right? So if we calculate the Newton's law, so F net would be ma, right? So F net would be how much? This would be mg sine theta equal to ma. So will cancel, acceleration would be g sine, right? So this will slip with this acceleration, right?
Yes, sir.
So this we learned, and then we talked about the dissipative forces, right? So then we talked about dissipative force, and the first thing that we talked about was this friction, right?
Yes, sir.
So we talked about two kinds of friction, right? One in the fluid and one in the solid. So the fluid one we called viscosity, and the solid one we called friction. And then we talked about three types of friction. One was this static friction, right?
Yes, sir.
And okay, so but before that we talked about two kinds of friction, right? One was this sliding friction, and the other was this rolling friction,
Yes, sir.
right? And this sliding friction was of three kinds. One was this static friction, and the other one was this
Limit.
limiting friction, and the other one was this kinetic friction,
Yes, sir.
right? And we also saw that this limiting friction is the maximum static friction. So this static friction was adjustable, and the maximum value that is this static friction can take is called the limiting friction, because after that the object starts to move, right?
Yes, sir.
So then we talked about the cause of this friction, and then we added this friction in our calculation, right? So let's say that we had this object, right? And this has, let's say, some force was applied on this object, right? And this is not moving. So then we calculated that there is some coefficient of the static friction, right? And there was some coefficient of kinetic friction. And I termed this as a coefficient of limiting friction, right? So
Yes, sir.
we saw that this friction was directly proportional to this normal reaction, and when we removed this proportionality, so we got mu L, L, right? So this was the limiting friction. Similarly, we got the kinetic friction, which was mu K L, right?
Yes, sir.
So let's say that we are applying this force in this direction. So due to the surface, there would be the friction in this direction, right? Let's say this is Fl. And we calculated all the forces and find out that when this object will start to, right? We did so many calculations.
Yes, sir.
Okay. So this was one case we took, and we also took this case on the inclined plane. On the inclined plane, let's say this is the object, right? And let's say this is not moving, right? So
Yes.
which means that there is some force acting on this direction, right? And there is some friction in this direction, right? Because if this is not moving, which means that this is friction is in this direction. But let's say if you are applying some force in this direction, right? Okay, so
Yes, sir.
I should draw it right. So we have this one, right? So then this object is experiencing this friction in this direction, and then we have this normal reaction and we have this weight, right? And this is with this angle. So then we calculated, because this was our mg, right? This was our mg, and this is the vertical, this is theta. So this was mg cos theta, and this was mg sin theta. So because this object is not moving, which means that this mg sin theta is balanced by this friction, right?
Yes, sir.
Okay, so this was the idea of the friction, and after that, we talked about the uniform circular motion, right? So we had two problems. One was the unbanked road, and the other one is this banked road. right? So let's say that in the uniform circular motion, firstly we calculated the angular distance, right? This was theta, and we calculated angular velocity omega, and we saw that this omega is related by this linear velocity by omega r, right? And we also saw that
Yes.
this centripetal acceleration was v square by r, which is omega square r. So these are the things that we learned, right?
Yes, sir.
Okay, so then we took two example of slipping of in the unbanked road and banked road. So let's say we have this circular track, right? And some cyclist, as you said, some cyclist is moving on this track, right? So
Yes, sir.
if he is taking the turn, right? So if it will slip, it will move in this direction, right?
Yes, sir.
But what force is acting on this object, which is helping this object not to slip, right? There must be some force which is acting in this direction, right? And that force we called was the frictional force, right?
Yes, sir.
Because these tires are experiencing some friction in this direction. That's why they are not moving in this direction, right?
Yes, sir.
And we said that because this is acting towards the center, right? So what is the force? So let's say this is our car on the road, right? This is
Yes,
the
sir.
car, and this is the normal reaction, and this is the weight, right? So this is the normal reaction. Remember, this is upward, not in this direction. This is normal reaction. This is weight, and or in the direction of the center, we have this frictional force. So this frictional force would be equal to what? Because it is in the direction of the center. This would be equal to what? Whatever force which acts in the direction of the center acts as what force that we have talked about in uniform circular motion. We talked about that whatever force which act towards the center, we call that force. Yes, you have forgotten. So let's say you have this uniform circular motion, and this object is, so let's say this is experiencing some force in this direction, and it reaches here, and this is experiencing some force. It reaches here and experiencing some force. So what was the force that we call that? Centripetal force, right?
Yes, sir.
Centripetal force, which acts towards the center, right? So this friction force is acting towards the center, so this would be equal to the centripetal force, right?
Yes, sir.
And as you already know, so what is the value of this frictional force? This is mu L mg, right?
Uh, so mg because n is equal to mg.
Yes, yes, absolutely right. So this is mu n. So this would be mu L mg. Yes, because this normal reaction is balanced by this weight, right? Because the car is not moving upwards, the car is not flying, right? So
Yes.
that is why this normal reaction is balanced by this. So N is mg. And then this force is centripetal force. What is the value of centripetal force? That is m into acceleration, AC, right? Force is
Yes.
ma, and AC we already know. What is centripetal acceleration?
So v square by r.
V square by r, right? So m and cancel, and we calculated the maximum speed with which the cyclist have to move in the circular track so that he doesn't slip, right? So this V max we calculated was root of mu L arch, right? This is the thing that we calculated, right?
Yes, sir. Yes, sir.
So do you have any doubt in this part?
Uh, so when they ask to check if he will slip or not, then what we have to calculate?
Yeah. So let's say that. Okay. So let us take. We did this question, right? And you guys calculated all the values. So let's say that takes a without the coefficient of will the cyclist slip or what. Good. So this is in the unbanked road. So this is the question, right? 4 point. Can you see the question? Should I zoom this question?
I can see it, sir.
Yeah. So you see that the cyclist is moving with 18 km/h, right? So
Yes,
the speed of cyclist is let's say 18 km/h, right? Let us find out. So this is in kilometer per hour. So we write it in meter per second. So how do we change that? Yeah, how do we change it in meter per second? So this is kilometer. How do we change kilometer to meter? That is
sir.
by 1000 meter,
Divided
right?
by 1,000.
And divided by 3600. So this would be meter per second, right?
Yes, sir.
Okay, so this double zero cancels out. This is 5 and this is 18. So you have this 5 meter per second, right?
Yes,
So
sir.
this is the speed of the cyclist. Okay, now as you asked that, how do we know that what should be this speed? So as we calculated that V max is root of mu s r and g, right?
Yes, sir.
So this should be the maximum speed of the cyclist with which he should turn his cycle, right? Otherwise, if he exceeds this speed, then he will surely slip, right?
Yes, sir.
Okay, so let us calculate this value. Mu s is given, which is zero point 0.1, right? And r is also given, which is 3 meter, and g we know.
10.
So this is 10 into zero point 0.1, 10, and this is 3. Right, so this would be root 3, which is 1.73 meter per second. Right.
Yes, sir.
So the cyclist should turn with which this velocity, right?
Yes, sir.
But he is moving with this velocity. So will he slip or will he not slip? What will happen?
So he will slip.
Right, he will slip because he is exceeding the limit. This is the limit that he should not cross, right? So this is the
Yes, sir.
maximum speed that he should turn the cycle with, right? So
Yes, sir.
this is the question. This is how they ask this question. So let us see, right? So how 25 meters, then the cyclist will slip, right? Okay,
Yes.
the condition is not obeyed. So we see that the condition is not obeyed. This is how they ask this question. Understood?
Yes, sir.
Okay, and then the second one is about this. So the second one is about this banked root. In banked road, you have this road which is tilted with this angle, right? So you have this road, and the car is moving in this road, right?
Yes, sir.
So the axle is, so let's say this is the theta, right? This is the theta. So this would be the normal reaction, right? This
Yes,
is
sir.
the normal reaction, and it is making an angle, this theta with the normal reaction, right?
Yes, sir.
And due to the surface, this friction is also acting on this surface, right, in this direction.
Yes, sir.
So we have, this is the friction, right? And then we have this weight which is acting in the downward direction, right? So you see
Yes,
that there would be no component of weight. Earlier in the inclined plane, we had this component of weight. But now we don't have any component of weight, right? Because this is in the y direction only. Understood?
yes, sir.
And but what is acting like a centripetal force? So the force which is acting in this direction, right, towards the center, this is acting like the centripetal force, right?
Yes, sir.
Okay, so then this is the angle. So if we write the free body diagram of this object, so we have this normal, right? We have
Yes.
this weight, and then we have this, right, this frictional force. Okay, so then this is theta, this is 90 minus theta, and then this is theta. Okay, so this is the overall diagram of the this bank road. Understood?
Yes, sir.
Okay, and this is F. So now you tell me that how many components would be there for this normal reaction. Remember, if you know this diagram, then all the things are clear. This diagram is very important, right?
Yes, sir.
So what would be this component? This is normal reaction along this direction. So what would be this component? This is theta, this is normal reaction. What would be this?
Sir, cos theta.
N cos theta, right? N cos theta. Yes, absolutely right. And what would be this?
N sin theta.
N sin theta, right? And remember, this is the direction of the centripetal force, right?
Yes, sir.
Okay, so, and again, you have this frictional force. So this is theta. So what would be this? This is theta. This is friction. So what would be this?
Uh, so what? Which one, sir?
This is theta. This is F, right? This is theta. So what would be this? This is theta. This is F. So along the angle, what would be this component? F cos theta, right?
Yeah, yes, sir.
And this would be how much?
This would be F sin theta.
F sin theta, right? So let us write this. This is F sin theta, and this is F cos theta, right? So now we have two equilibriums, right? One would
Yes.
be one would be this vertical one, right? So the vertical, let us write the vertical component, vertical part. So vertical part would be, if you write, so in the y direction you have n cos theta, and in the downward direction you have f sine theta plus mt, right? This is the
Yes.
vertical part. And this is in this direction, whatever force is acting in this direction towards the center, that will act as the centripetal force, right? So
Yes.
the horizontal part. Are you tired, Ram?
Uh, little sir.
Yeah, you are feeling little bit sleepy. So, okay, so I will just discuss this part and then I will end the class, right? Then you take rest and prepare all these chapters. Okay.
Yes, sir.
Okay, so then the horizontal part from here, you tell me what would be the horizontal part?
Uh,
What are the forces that are acting towards the center?
F cos theta.
F cos theta and
N sin theta plus.
F cos theta, right? So,
Yes.
so the N sin theta plus F cos theta. These forces are acting towards the center. So this would be centripetal force.
FC.
Understood?
Yes, sir.
So this is our second. And when we solve, so let's say this is n cos theta minus of f sine theta. This is mg, right? This is our first equation. And n sine theta plus f cos theta. This is fc, right? Which is mv square by r, right? Alham.
Yes, sir.
So then what we do is that we divide these two things. So we divide second equation by first. So mv square by r divided by mg. This would be n sine theta plus f cos theta divided by n cos theta minus f sine theta. Right. So m cancels, and v square by rg, this would be n sine theta plus f cos theta divided by n cos theta minus f sine theta. So can you tell me, do we know the value of this frictional force?
Yes, sir.
Do we know this value of friction?
Some uh, mu
Mu
uh
ln.
ULN. Yes, sir.
So v square rg is n sine theta and mu ln and cos theta, and we have n cos theta minus mu ln sine theta. So what we can do is that we can, this n is common everywhere. So we can take out this n. This would be sine theta plus mu l cos theta. And if we take n from here, so this would be cos theta minus mu l sine theta. So n cancels, right?
Yes,
And
sir.
uh, and then what we do is that this is sine theta, cos theta, sine theta, and we want to write it in the terms of tan theta. So how can I write sine theta as tan theta? What will I do to sine theta that it becomes tan theta?
So sine by cos.
Yeah, so I divide it by cos. So dividing dividing every term by cos theta, right? So this would be v square rg, this is sine theta by cos theta plus mu l cos theta divided by cos theta minus mu l sine theta by cos theta, right? So this is then this will become tan theta plus mu L.
So why do we want tan theta here?
Yeah, because these are different quantities, right? Sine theta, cos theta. So I want it to be not I, but conventionally we want it to be consistent, right? Only
Yes,
one trigonometric function. So then this would change it to tan theta. So then we have only this tan theta, right?
yes, sir.
So then if I write it like mu L plus tan theta and 1 minus mu L tan. So then I take this Rg in the right hand side. So this would be Rg multiplied by mu L plus tan theta divided by 1 minus mu L tan. So then this V becomes, this is max, right? Because I have used this mu L, right? So
Yes,
then
sir.
this would be root of Rg and mu L plus tan theta and 1 minus mu L tan. So this is the speed with which the cyclist has to move so that he doesn't slip, right?
So for banked road, right?
Yeah, for Bangalore. So this is for the case of Bangalore. Okay. And we also calculated this optimum velocity. So this optimum velocity reduces the wear and tear on tire, right? So
Yes, sir.
this optimum velocity, what does it do? So it just neglects this, right? So it neglects this frictional part, right? So we move the or we turn our car or cycle in such a way that it doesn't experience frictional force, right? So
Yes.
when we do that, and then that speed is called the optimum velocity. So V optimum would be how much? This would be Rg, and this is zero. So that would be tan theta, and in the new denominator, what do we have? This is zero. So the whole term is, this is zero, so this is one. So we have this V optimum. Right. So to reduce the wear and tear on tire, we move with this velocity.
So what do we have to use this for in the question?
Yes. Again, so let us go back to this NCRT problem, right?
Yes, sir.
So, so yeah, this is the okay. So as I have written in here, right?
Yes, sir.
Okay. So to reduce the wear and tear, with which velocity we have to move? Optimum velocity, right? And to skip the slipping, right? We have to move with Vmax.
Yes, sir.
Okay, so to avoid slipping, we have to apply Vmax and optimum we already know, right? So, okay. So this is the question. A circular racetrack of radius 300 meter is banked at an angle of 15 degrees. So theta we know, right? R we know.
Yes, sir.
And what else do we know? If the coefficient of friction of race car and the road, so mu s we know, right? So what is the optimum speed? So to calculate the optimum speed, V optimum, we calculated that this is Rg tan theta, right, Alham?
Yes, sir.
So R we know, R is 3000, right? G we know, this is 10, and tan 15. So how much is tan 15? How much is tan 15? Hmm. So tan 15, let me use the calculator, right? So tan 15, tan of 50.5, 10. So this is, let me write it as tan 45. So tan 15. This is 0.2679, right? So tan 15 is 0.2679. Okay. And when we calculate this value, so when you multiply this with, let's say, 3000, and you have one more zero, so 30,000, and then you take the root, right? So
So when
then,
we were doing this in class, you changed the angle.
yeah, because you don't know the value of tan 15, right? So
Yes,
when I was doing this problem, I gave you the angle which you already know, right?
yes, sir.
So yeah, so then this is 89.65 that you will get meter per second. So this is V optimum. So this is the speed with which the cyclist has to move so that his tire doesn't wear and tear, right?
Yes, sir.
So 80, how much? Oh, so Rg tan theta 89. We are getting 89, right? And Y they are getting 28.1. So they are getting 28.1. Oh, I have written 3000. So this is 300, right? Not 3000.
Okay, sir.
So this is 300. Then what we will get? So then what we will get?
So
300.
they have taken G as 9.8.
They have taken 9.8. Yeah, so whether we take 9.8 or whether we take, did they mention that we have to take 9.8?
No,
No, they have
sir.
not. So then we can take to avoid the complexity, we can use 10, right?
Yes.
So 300 and then 3 into 10 and into 0.2679. So this is 803 and root. So 28.34, right? 28.34 meter per second. And how much they have got? So they have got 28.1. So that is the difference of 9.8 and 10.
Yes, sir.
So there is not so much of difference, right?
Yes, sir.
Okay, so this is V optimum. And we can also calculate the maximum permissible speed, right? V max would be how much? This would be root of Rg and then mu s minus plus of tan theta and 1 minus mu s tan theta. Right.
Yes, sir.
So this tan theta we have already calculated, right? How much was that? So tan theta we calculated. This is 300. This is 10. Mu s is 0.2 plus 0.2679 divided by 1 minus 0.2679. So how much would be this? This would be 0.2 into 0.2679. So this is 3000, right? And this is 1 minus 0.053. And this is how much? 0.4679. So uh, 1 0.4679 divided by this would be how much? So 1 minus 0.053. So this is 0.000. So 7952 and this is 9. So 0.92. Okay. So 7 and 954. So 0.947. Right. Divided by 0.947. So this is 0.49 into 3000. So this would be how much? So this is root of 1482.2597. And when we take the root, so root of this is 38.5. Right. So
Yes, sir.
this is the speed with which the cyclist has to move so that he doesn't slip. Right. And
Yes,
in the answer, they are getting 38.1 because they have used 9.8. Right.
yes, sir.
Okay. So, any doubt in this fourth chapter?
No, sir.
Okay, so then we will stop it here and you take rest and prepare the rest of the chapters, right? And do some numericals also, right? So this was the idea of this chapter, right?